In step 3 now of the slope deflection method application, we write the equilibrium equations, one per each kinematic degree of freedom. Now note, I've already done a whole lot of work here on the free body diagrams. I've shown the member, in this case with the applied load, the member end moment shown in the positive direction on the member end. This is crucial. Do not draw these the way that you anticipate that they might physically be acting. Instead, you must use the sign convention. And we have chosen to use clockwise as being positive on the member end. You'll see why that was a fortuitous choice, why some people like that approach here in very shortly. Right? So clockwise positive on the member end. MAB at end A, MBA at end B of member AB. Right? I've also gone ahead and shown the end shears, VAB, VBA. At this step, these are not particularly needed or used at all. We're really just going to focus on these member end moments. Again, you'll see why that's the case here in just a moment, pun intended. So now we have this other member, it has no member loads on it, it just has the member end forces. Again, crucial, you must show the member end moments in the clockwise fashion, that is the positive on the member end. Here's why: because we're going to take the statically equivalent effect and flip it over onto the joint. Right, so now they'll look like so, and you'll say, well, that can't possibly be the way it works, because if so, they wouldn't be in equilibrium. And that is certainly true, but we will take care of that here, because the equilibrium equation that we care about is going to be this one associated with the kinematic degree of freedom, which was not C, I wrote C there, but at joint B, we didn't know theta B. That was the only kinematic degree of freedom. So we're only going to write one that's associated with a rotation. That would be a moment. Right? And this is infinitesimally close to the joint, so the shears that I've drawn here don't play a part. And so all we have, and it's going to look like this format every single time for a rotational degree of freedom, is that MBA plus MBC is going to be equal, well, static equilibrium. There's no applied moment at the joint, so it's equal to 0. Notice here the subscript. We're at the near end. We're at the B end, so it always shows up first. And all these others are the far ends of every member that frames into the joint. So if I had 3 members in, I would just be adding that MBD. The fourth member, MBE. And so on and so forth. If I had 20,000 members rigidly connected to that joint, I'd have 20,000 of these, all summation of MBI, blah, 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 all the way up for all the members, and it would equal 0, again, unless I had an applied moment at the joint, which then would make that non-zero. Nice and simple to program. And that's it. Because from there, then, what we do is we substitute in the MNF equations. Now I've rewritten them here just so we don't have to go back in the paper to find them. But so here's the MAB equals 4EK theta B minus WL squared over 12. That's the fixed end moment term. Here's the MCB term. Neither one of these show up in our equilibrium equation. The only one we got, or I should say the only two we have, are the MBA, MBC, the ends of the members actually connected to the joint. So MBA, MBC. So all we do is drop these in there. We've got 8EK theta B plus WL squared over 12. That's MBA, plus then the MBC term, that's 4EK theta B, and that's equal to 0. One equation, one unknown, we have 12EK theta B. It's going to be equal to a minus WL squared over 12. So therefore, and I would probably only do this in terms of EK theta B, and you'll see again there why I want to do it that way in a moment. That's going to be equal to minus WL squared over 144, and now we have the value of the rotation. Notice it's negative. That's interesting. So it wasn't clockwise rotation, it is a counterclockwise rotation, which is something that we had guessed from the very beginning. Right? So we're going to use that information in our next step to go find the member end moments.